Take you through a number of different ways in how you can apply this for image acquisition, image segmentation, but also learning something about the data you operate with, for example, for discovering biomarkers in your data. Okay? And I'm going to start with an example which comes from image acquisition. I'm going to show you two different approaches, one using dictionary learning and one using manifold learning. And you can later on, you can decide for yourself which one you prefer most. Actually, it turns out one is much faster than the other one. Okay? So why do we actually want to do anything clever with the image acquisition? So if I look at, for example, one image modality like MRI imaging, it's a very powerful imaging modality. It's really good, but it's very, very slow because I have to acquire my data inherently in a sequential fashion. Okay? And that slow acquisition is good if you're looking at the brain, at the bones. That's not a big problem, but if you're looking at moving objects, it actually becomes very inefficient. So if I do, for example, imaging of the heart, I need to do, for example, something like gating. That means I only acquire data from the heart when it's in a particular state during the cardiac cycle. And that slows down the acquisition significantly. So here's an example of the data set I want to acquire. And as I told you, I have to acquire, it's a sequence, I have to acquire every frame of that sequence dynamically. And that's very important in order to, for example, allow us to do functional analysis of the cardiac contraction. Now, if I want to explain to you how MRI imaging works, I could use this sort of example here, but it's not a very good model of what happens in an MRI scanner. But for the moment, I want you to only remember one particular aspect about MRI imaging, and that is that the image acquisition occurs in something which we call K-space. That K-space is effectively the Fourier transform version of the image. And what I can do in this K-space is I can go line by line, acquire all the measurements of frequencies which the image contains, and then I can simply apply a Fourier transform to go back to the image I want to recover. Okay? So it's a very simple operation, just a linear transformation of my K-space data. Now, why is MRI imaging so slow? Actually, acquiring one line is a fairly rapid process, but going from one line to the other line, it's a fairly slow process because of the hardware or the physics limitations which I have in an MRI system. Okay? I can do many things like parallel imaging, but still I have the fundamental limitation that I have to traverse this K-space line by line sequentially. Okay? Now, if I acquire another time frame of the heart, I need to do the same thing again. I need to sample the same K-space again and have to repeat this. Okay? So this becomes a very time-consuming, slow process. So how can I speed up the acquisition of my data? Well, there's a very simple trick. Okay? I'm just going to undersample my data. So instead of acquiring the full K-space here and reconstructing the image, I'm just randomly sampling K-space, and I'm going to end up with an image which is, if I only sample 25% of the K-space, I'm going to end up with an image acquisition which is suddenly 4 times faster. That sounds brilliant, and actually it's very nice, but if you look at the image, unfortunately you can't see it very nicely on this projector, it's aliased. Okay? And that's not a big surprise because what I'm doing here is I'm violating Nyquist sampling theorem. So obviously I'm going to get some artifacts in the data. So I can accelerate the acquisition by undersampling, but I end up with a much corrupted image. Okay? So what I'm trying to do in the next couple of slides is to come up with a way of estimating the missing K-space which removes all these artifacts and recovers a fully sampled image. Okay? And I'm going to show you an example which uses sparse coding or dictionary learning for this application. And then I'm going to show you how you can also do the same thing with manifold learning. Okay? So the assumption is that the data which I have, and I'm going to, at the moment, deal with 2D images over time. So I can view them as a 3D stack of images, but the third dimension here is not space, it's actually time. Okay? I'm going to make the assumption that the original image is compressible in some form. That means I can apply a transformation, a sparsity transformation, and I can represent the image using a very small number of coefficients after I have mapped it into this spatial, in this sparse domain. Okay? That means that most of the coefficients here are going to be 0. Okay? Now, what happens if your image is corrupted by these aliasing artifacts? Well, it turns out that the signal is no longer sparse. So if I take my corrupted data, I apply the same sparsifying transform, I end up with something which is much less sparse. And the reason for this is I need to encode all the aliasing I have in the data. Okay? I need to now spend much more time encoding the aliasing. And that means if I really want to make this not sparse, I should also use an undersampling pattern which produces incoherent aliasing. So that means really random aliasing, because the more random it is, the more energy I need to spend in encoding this information. Okay? So now the idea of recovering this image from its undersampled corrupted version is quite old, and it's called compressed sensing. And it can be formulated in a nutshell like this. I'm going to assume that I have my undersampled data in K-space, and I have my undersampled Fourier operator, and I'm trying to recover the full image or the full K-space. So X here is now no longer in image space, but in K-space, in such a way that this full solution X is consistent with whatever I have actually acquired in K-space. That means for those data points which I've acquired in K-space, I want the Fourier version of the data to be similar to this. But at the same time, I want a signal which is as sparse as possible. So I want to find a sparse solution of the data as well. Okay? So you can simply formulate this as an energy function and optimize this energy function. And what that actually means is I'm solving this optimization problem, find the sparsest solution, subject to the fact that my solution is consistent with whatever measurements I've made in K-space. And if you view this, you can sort of view this, your initial image, which is your corrupted version of the image, is somewhere here in this energy or optimization space. And I'm going to optimize it so that I'm going to find the sparsest solution X star here, which is what I want. Okay? So this formulation has been proposed by Michael Lustig a couple of years ago, and is really a powerful approach for MRI reconstruction. Okay? So most approaches which follow this idea use a fixed basis for doing the sparsification. Okay? So the sparsity transform can be, for example, a wavelet transform or a DCT transform, and that's what's been used in most of the literature. However, we can also decide we want to learn what is the optimal sparse basis for representing the signal I'm acquiring. Okay? And so we're going to use this, we're going to use dictionary learning as a sparsity transform to try to recover the sparsest possible solution from our signal. Okay? So the idea I'm going to go through is very simple. It consists of 3 different steps. I'm going to acquire my corrupted data set. Yeah? So this is effectively just randomly undersampled data, and everything which I've not sampled in K-space I'm going to fill with zeros. I'm reconstructing the image from it, and then I'm training a dictionary on these motion corrupted or on this artifacted data. I end up with my dictionary. I sparse code the image using this dictionary. I go back into Fourier space and make the data consistent between with the measurements in Fourier space, and then I'm reconstructing a new version, learning a new dictionary, and going through the chart again. So I keep on doing this until the solution I reconstruct no longer changes. So until this image really doesn't change anymore. Okay? And so the first step is the dictionary learning, and here it's quite important that I'm going to do this in space and time. So I'm going to take my 3D stack of images, so 2D plus time. I'm going to extract patches from the image. So these patches are effectively just square regions in the spatial dimension and then have a certain length and time. I'm going to stack them into these long vectors in this matrix, and I'm going to randomly extract these patches from all over the image. Okay? And now what the dictionary learning tries to do is to find a sparse representation of this matrix, of all the patches in the images, using this dictionary plus a set of sparse coefficients. Okay? So what I'm actually doing is I'm optimizing not only those coefficients, but also the dictionary elements here. Yeah? So I'm basically optimizing both at the same time. And I'm going to try to approximate the original patches in the image as much as possible. Okay? So here's a dictionary, an example of the dictionary atoms you would get if you do this with a cardiac MRI scan. And you see that they're changing the dictionary atoms because, of course, I'm showing you these dictionary atoms in space and time. Okay? So you can do this using, for example, KSVD or any other dictionary learning algorithm. Actually, we use a KSVD algorithm for this. Okay, so once I've learned the dictionary, the next step is a sparse coding of the data using the dictionary. Okay? So here what this Rj is simply an operator which extracts a patch from the data, and then I'm going to minimize the distance between what I reconstruct from the dictionary and the original patch I have in the image, subject to my sparsity condition. And what this does is effectively a denoising step of the image. Yeah? So if you want to view this as an image processing operation, you can view this sparse coding as denoising your data using the dictionary you've just learned. Okay? And it's denoising because the dictionary, together with the sparsity constraint, cannot perfectly recover the data you give it with. So you actually tend to exclude the aliasing, which is exactly what you want from the dictionary learning. Okay? So in computer vision, most people would use dictionary learning for denoising or for in-painting or for other applications, and effectively we're leveraging the same effect which it has in denoising here to get rid of the aliasing of the data. Okay? Okay. So the final step, which I still need to do, is because of course now I've denoised the image. How do I know that the denoised image is actually a representation of the true object I'm trying to recover? So what I'm going to do now in the final step is I'm going to go back from image space into K-space. So I'm applying the Fourier transform. And now I'm going to basically fill in all these holes in K-space which I have, all these lines which are missing. I'm going to estimate them with what I've just obtained from the Fourier transform of the recovered image. And if I have got a line acquired in K-space, I can blend that line with in K-space, with my estimate from the denoised version. And that, of course, I should only really do if I think that my K-space measurements are noisy. So if my K-space measurements are perfect, I should just keep the K-space measurements. But if they're noisy, I can basically average the estimated version of K-space with the measured version of K-space with a certain scale factor. Okay? And then I end up going back into image space, applying the Fourier transform again. I get back my recovered image. After I've done this, I start all over again. Okay? I keep on doing this until I have no longer a solution which changes. So here are some examples of what this looks like in practice. And I'm sorry you might not be able to see this very clearly. So this image here at the top is your fully sampled MR image which I've acquired. The image here at the bottom is what happens if I throw away 7/8 of the data. So I'm only keeping 12%, 12.5% of the data. Everything else I'm assuming is 0. And I'm recovering an image from it. So you can see that this image looks really blurry, has lots of artifacts in it. This image is what I actually obtained from the compressed sensing reconstruction using dictionary learning. And if you compare these two images, the fully sampled version and the undersampled version recovered from this, if I show you the error map, you see very little error in these reconstructions, okay? So this here is, on the right-hand side, is a competing compressed sensing method which uses a fixed basis. And it's not quite as good. You see, actually it produces more errors in the error map than the dictionary learning method, because that has a dictionary which is optimized in terms of this data I've just acquired, okay? So this shows you how much you can actually recover from your data using dictionary learning. You can actually push this even harder. You can even go to 12-fold undersampled reconstruction. If you would see the image on the screen here, you would see that they still look very similar. I now get higher errors because I've undersampled the data so aggressively, but still the dictionary learning does a pretty good job at trying to recover the data from this, okay? So there's only one drawback in all of this. The dictionary learning is a really, really slow process. It takes a reasonable amount of time. And the most important thing I should also highlight is that we're learning the dictionary on the data we have acquired. So I'm making no assumption about what the data will look like before I acquire it. So it's not like I've learned this from a population of subjects and then I'm going to apply the model. I'm just going to apply the model directly to the data I've acquired. So there is no a priori assumption about what the data might look like, except that I can sparsify the data, okay? But that has a drawback because I have to do the dictionary learning online every time as I acquire the data. So you can also do something similar using manifold learning. And it turns out that this is a much, much faster approach. It's not quite as good, but it's actually a very, very fast approach, okay? And I don't think I have to explain you again what manifold learning is or how it works. I'm going to use the Laplacian eigenmap view of the world, where I'm going to take all my data, I'm going to compute a matrix, sparsify the matrix, and then do spectral analysis on that matrix. But I'm going to do that with data which comes from k-space of images. So assume that I have an image of the heart. Here, this is a free-breathing image sequence of the heart where you can see the heart beating, but also the patient is breathing constantly during the acquisition. And what I'm going to try to do is undersample that data set so I can acquire it quicker as before. But I'm going to learn the manifold structure of that data using this Laplacian eigenmap idea. And the manifold structure of the data is actually not learned in image space, but I'm going to go into k-space, and I'm going to learn that manifold structure of the data in k-space, okay? And so if I learn that data, you probably see that the data will lie along in 2 dimensions along this curve, and this curve somehow represents both cardiac contraction as well as breathing motion as the 2 degrees of freedom, okay? However, it turns out that if I construct a manifold only from the central lines of k-space, I get virtually the same manifold structure, okay? So I can actually learn this manifold structure only by acquiring a few lines of k-space, okay? And that's actually what's a quite powerful approach in this particular example, okay? And just remember that why I'm using the center of k-space is because the center of k-space contains the low frequencies and therefore the most energy in the image. So this is something which I will always sample, and I'm just going to randomly sample the high frequencies in a random fashion. Okay? So what I'm going to do is I'm going to acquire this K-space. I always sample the center of K-space. I'm going to apply Laplacian eigenmaps, find out the manifold structure, and then I'm going to use simply a kernel-based regression to interpolate the missing lines of K-space, which I've randomly sampled in every time frame, from the nearest neighbors in the manifold. Okay? So in order to get the unknown lines of K-space, which I've not acquired in this particular frame, but I might have acquired at some other time point, I'm going to apply basically this kernel-based regression using a Gaussian kernel, but using manifold coordinates as your weights for the kernel regression. That means I'm going to use an interpolation which will look at automatically at data points which are acquired at a similar cardiac phase and a similar respiration phase. Okay? So this here is not compressed sensing. This is effectively a clever way of interpolating K-space from neighboring samples. Okay? And what happens here is if I acquire my data, my undersampled data, and if I'm going to interpolate the missing points in K-space from its nearest neighbors, I can recover virtually a perfect version of this free-breathing image. And I can do that in a very efficient way because I'm just doing interpolation. I just have to find a mapping of my data into a manifold space. However, that manifold space, I think this contains 200 images. It's a 200 by 200 matrix, so it's very, very quick to calculate. And I can do this very, very efficiently. I don't have to learn any dictionary. I can probably do this in real time. I think I can definitely do it in less than a second per frame. And so this way of using manifold learning, here's another example with an 8-fold undersampling, is a quite different view of recovering the original signal, but it's a very powerful way because it's something which you can do in real time, whereas the dictionary learning probably runs for a couple of hours, even with GPU acceleration, to recover the full image. Okay, I'm now going to switch gears a bit. I'm going to start talking about image segmentation and how we can use manifolds and dictionaries for image segmentation. And in order to do this, I want to give you a very simple view of a very popular approach for image segmentation. And that approach to image segmentation is simply treated as an image registration problem. So if I have an atlas or a model of my anatomy, you can view this simply as a labeled data set. If I have a labeled, for example, brain or a labeled scan of the heart, I can interpret my new data set simply by registering this atlas model to my new data set and propagating the labels into that new data set. Okay? So that's a very simple view of the world and would work perfectly if I have a perfect image registration algorithm. Okay? So here's an example of how I can warp, for example, one image onto one brain onto another brain's anatomy. But if that registration process would be perfect, then I could actually do a really good job at doing this. Now, it turns out that, unfortunately, no registration process is really perfect. So I'm always going to make some mistakes. And even if you do a very careful design of a registration algorithm, you're going to end up with making some mistakes. So, for example, here you see some differences between a manual segmentation and automatic segmentation. If you look at this on the first glance, it looks okay. If you start looking at details, you will discover many, many small mistakes in this. Okay? So if I have multiple atlases, I can start doing something which is more similar to a sort of learning-based approach. I can take these different data sets and view them as training samples. but I can still do a very naive way of dealing with the registration, with the segmentation problem. And that very naive view of the world turns out to be quite powerful. So I take all my training samples, my atlases. I'm going to register every atlas to all the to the unseen data, to the unseen image which I'm trying to segment. If I repeat this process for all my atlases, then you end up with multiple different segmentations. So you end up with slightly different segmentations, and the reason why they are all slightly different is because you're going to make a small mistake in these mappings between atlas and your image. In addition, the manual expert probably has made slight mistakes in annotating the ground truth, so none of them are perfectly annotated, and of course the anatomy is also different in every subject. So if you want to take a machine learning view of the world, you can say actually these segmentations are all the output of a classifier, of a very simplistic classifier which uses some magic registration inside. If you have multiple weak classifiers, one way of building a better classifier is to simply fuse them together, okay? And the earliest versions of these algorithms, they simply did something very, very simple. They simply said, actually, let's do majority votes, correct? For every voxel here, I'm going to look at what the different classifiers say, and I'm going to agree with the majority of my classifiers, okay? It turns out if you do this, even though it's quite naive, you can improve the performance of your segmentation drastically if you increase the number of images you have as labeled training data. And it turns out that even though you get in the beginning a very big improvement, as you go on, your improvement gets less and less strong. And that's a bit disappointing because you would think that the more training data you would have, your system should get better and better, okay? And it's obviously not the case here. So now there are multiple different ways of improving this, this very simplistic scheme. One simple answer is brute force. And brute force always works well in imaging. If you can get enough training samples, if you can, for example, get 300 labeled brains, instead of using all 300 images, what you can do is you can actually say, well, let me register every image purely with an affine transformation onto my standard space, for example, an average coordinate system. And then I'm going to register also my unseen data to this standard space coordinate system. After I've done this affine coarse registration, I'm going to choose which of my images are similar to the image I'm trying to segment. And I'm only going to use those images which are very similar to the image I'm trying to segment. I'm going to register them very carefully using non-rigid registration, and I'm going to do my decision fusion here. And obviously this works better, correct? Because this is effectively using a k-nearest neighbor interpretation of your classifier. Instead of using all images, you're going to only use your k-nearest samples, which look most similar to the image you're trying to segment. Now, if you look at, for example, how well does this approach do, you now get a very different behavior. So let's assume I have around 250 images, and I'm going to do the naive approach of randomly choosing some images from my database and fusing them. In the beginning, you see a massive improvement, but then you're completely flat. The more data you throw at it, nothing will get better. In the blue curve, I'm going to only use the nearest neighbors, and I'm just going to vary how much nearest neighbors I'm going to use. And you can clearly see that in the beginning, I get an even bigger improvement. I now get here to the maximum, and then as I increase the number of nearest neighbors, actually my performance goes down. And again, that's expected. The blue curve and the green curve will meet if I use all my data because they are effectively the same approach in the limit, okay? So this approach tells you what you should really do is get huge amounts of data and then only use the nearest neighbors. Okay? So that's an interesting conclusion, but of course it has a fundamental limit. The conclusion from this is you should get as many labeled data sets as you can, and then only use a few of them, the ones which look most similar, to do the segmentation. However, that's just not feasible. If you're working with a clinician and the first thing you say to the clinician is, yes, I can solve your problem perfectly, but you need to give me 10,000 data sets which you have manually annotated. They're just going to walk away and they will never talk to you again. So is there a solution? Can we do something more clever? Can we find a way of bootstrapping the problem effectively? And I'm going to show you two approaches which use a relatively small amount of data to try to overcome this problem. Okay? The first one uses manifold learning again, so not a big surprise here. But I'm going to show you, let me start off with this example. So when we started trying to deal with this segmentation problem in the brain, we tried to use these atlases which I've shown you before. And it turns out, unfortunately, you can't see the atlases very well. They're the green points here in this manifold of images. And the green points are all clustered here to the left-hand side. Okay? And all the other images which we're trying to segment, they come from patients which have dementia, which are old. It turns out that these images we're trying to segment, they are quite different from the images we have which we have labels for. And that's a problem because obviously these images look like outliers for the rest of the population. Okay? And actually the real reason why they probably look like outliers is because all the atlases which we have, they come from a number of students at Imperial College. They're all computer science students, so they're probably all outliers by definition. But they're all quite young subjects, so the brain looks a bit different. So if I'm trying to use this atlas here to label this brain here on the other side, I'm going to have a hard task because the images look very dissimilar. Okay? So first of all, how do I construct this manifold? I should have said this. We are only interested in a structure called the hippocampus, which is very important in aging brain. So I'm going to define similarity between all my images by restricting my similarity measure to a small region around the hippocampus and then computing similar mutual information between all pairs of images. Okay? The resulting mapping of my manifold, if I force the manifold to be reduced to 2-dimension, will look like this. Most of the subjects are clustered here. The blue ones are the subjects which have Alzheimer's disease. The red ones are just normal controls, but also aging population. And the green subjects are here on the left-hand side. Okay? So how do I use this manifold now to help me with the segmentation? Well, I'm going to use the following idea. I'm going to use my labeled data, which are the blue points here, and I'm going to only label those brains which are close to the population of labeled brains. So I'm going to select the nearest points, these green points. I'm going to label those by doing multi-atlas segmentation, so what I showed you before. And of course, after I've segmented them, I have a larger population of images. I'm going to iterate this process until I've segmented every image in the population. So what I'm really doing is I'm propagating the information through the manifold step by step, rather than trying to propagate the information in one go to every subject. Okay? Of course, in practice, I need to take care that these images which are newly labeled, that they don't contain mistakes. So I'm going to do a EM-based segmentation refinement at every step to make sure that I'm going to not propagate obvious segmentation mistakes. But otherwise, I'm just going to do effectively this procedure. And if you look at the results, if you look at the whole population, remember that the atlases are outliers. If I look how well does my algorithm do for segmenting subjects which are very close to the atlases, you can see I'm actually doing very well in terms of segmentation performance. If I go to the population which is the most dissimilar, then the bottom, the blue line here is the one which represents what would happen if I just do naive multi-atlas segmentation. So I'm going to go, the performance decreases significantly. However, if I do this manifold label propagation, I end up with a result which is virtually the same performance, even though these subjects are quite dissimilar to the subjects I have in my manifold. Okay? So just going to show you very quickly another example how you can tackle the same problem with dictionary learning. The idea here in dictionary learning is based on something which is called patch-based segmentation, which has been proposed a couple of years ago. And here the idea of trying to label a pixel in an image is simply transformed into a reconstruction problem. I'm going to extract a patch around this voxel in the image. So this patch is just a patch of gray values. And then I'm going to go through my atlas database in the same location, and I'm going to search in the neighborhood of each atlas for patches, and I'm going to build what we call this patch library. So this patch library is going to contain a set of patches which hopefully some of them are going to be similar to the test patch. And I'm going to now fuse all these patches together from my patch library so that I reconstruct the intensities in my test patch. I'm going to use the same weights to estimate the label of the central pixel. Okay? And then I'm going to go on to the next pixel and keep on doing this. Turns out that I can solve this problem even better if I, instead of basically fusing all the labels together, or all the patches together, I can do only a sparse combination of these patches. But even better, I can summarize the whole patch library using a dictionary. Yeah? So that instead of having to search through all the patches in my neighborhood on the fly, building this patch library on the fly, I simply learn a dictionary from my labeled data, and I'm going to have a gray level dictionary plus a label for that dictionary atom. I'm going to code this patch sparsely using the dictionary, and then I'm going to use the weights to look at what the label for this central pixel should be. Okay? So if you want to view this more mathematically, you can sort of say, actually, let me extract all the patches from my image. I've learned the dictionary. I'm going to sparse code this dictionary using this parameter vector, and that gives me a reconstruction of my patches, and I can try to use the weights from this to reconstruct what the labels should be. It turns out if you do this, it will not work. Okay? And the reason for why this doesn't work is because this dictionary learning is very, very good at reconstructing your signal, so reconstructing the patches, but I don't have a unique combination of this reconstruction, correct? My dictionary is overcomplete, so I can achieve the same reconstruction in multiple different ways, okay? And that means it's not very discriminative. It's very good for reconstruction, but it's not very good for discrimination. It turns out I can do a simple trick to transform this dictionary learning into something which is more discriminative. And I'm going to do this by adding a very simple linear classifier, or my labels to, I'm basically adding labels to my patches here. I'm going to learn a very simple linear classifier as part of the dictionary atoms, which will give me my labeled or my reconstructed labels as well. So in addition to learning a gray level dictionary, I'm now also going to learn this very simple linear classifier, and I'm going to add this all together and optimize this whole problem over the gray level dictionary, my linear classifier, and my coefficients for the reconstruction, okay? And then when I do the classification, I'm simply going to compute what my linear classifier tells me, given the sparse coefficients. I'm just going to take the label which gets the highest vote from the linear classifier. So this is called discriminative dictionary learning, and that works actually really well for segmentation. Here are some examples of how you can segment, for example, the hippocampus of an elderly subject using a patch-based label fusion approach, sparse reconstruction, and dictionary learning and sparse reconstruction. And this turns out to be the best approach for this experiment. So I'm going to finish off with a few more slides on something which is more sort of machine learning, core machine learning application, which tries to discover biomarkers from images without actually segmenting them, without registering them, really just trying to discover what's in your data. And if I wanted to use manifold learning, I guess you have seen this now a couple of times, then I would simply take my data, compute my dense matrix, sparsify the matrix, do my spectral clustering, and for example, I could say, well, if I do this with brains of patients which have Alzheimer's and brains of healthy patients, perhaps I should actually end up with the right solution. However, one thing which is a sort of challenge is to identify which region in my image should I look at. Because if I take the whole image, then I'm going to basically, for example, find out that some people have larger heads, larger brains than other people, and I also might find that some people have large ventricles. This is not what I'm actually interested in. So one option is to say, actually, I'm going to look at certain regions in the brain, and I know a priori that these should be important regions. But the other approach is to learn directly from the data which regions are actually useful regions to measure similarity in. So one thing is I can, for example, say I can use a sparse regression model, for example, an elastic net, which has a sparsity term and a grouping of voxels, and I can say, actually, tell me something about where is the data different between patients which have Alzheimer's disease and patients which don't have Alzheimer's disease. And I'm going to learn a region in the brain which is interesting for trying to do manifold learning with. So what happens if you do this? You actually find out that there is a very significant region in the brain which is different. For example, you get these voxels here in the hippocampus having a very high significance. Actually, that's not very interesting because you knew that beforehand, but it confirms that even if you use a data-driven approach, I can automatically learn which voxels in the image are actually interesting, for example, for subsequent manifold learning. If I then do the manifold learning, then in the first instance, you're going to be quite disappointed because you're going to work out that the subjects which have Alzheimer's disease, the blue ones, and the normal controls are all scattered around the manifold. If you wanted to train a classifier here, you wouldn't really get very much joy out of it. However, if you have longitudinal data, so if you know, for example, for every subject, how they change over time, you're going to, you can also put that longitudinal information into the manifold. And suddenly, you're going to start to see a behavior that all the AD subjects, the blue ones, they start in this part of the manifold, but they then move towards the left in the manifold. And turns out that if you use this longitudinal information and the manifold coordinates as an input to a classifier, you can do very accurate differentiations between normal controls and people who have dementia. So I want to show you one final example how you can also add additional non-imaging information into the manifold, because that's actually something which you should all consider. If you do medical imaging, not all the information you need about a patient is going to be in the image. There's going to be lots of non-imaging information, clinical records, genetics, whatever you want. But you can incorporate that all into the manifold quite easily. And for that, it's quite interesting to, for example, take a graph view of the world again. So if I compute a similarity graph of my images, and for example, if I have genetic information, somebody is, for example, ApoE positive or ApoE negative. ApoE is a gene which increases your chance of developing Alzheimer's disease. I can incorporate that quite easily into that graph structure. So I can, for example, take all the subjects which are ApoE positive. I can connect them to this special node in my graph with a fixed weight. And all the subjects which are ApoE negative, I connect them to this other node. And effectively what this does is you're changing your cost function you're learning for the embedding. Okay? That cost function now has a specific term which weights these connections to these special vertices which don't really correspond to images but correspond to non-imaging information. How you should choose a weight is another matter for discussion, but you can quite easily incorporate this extra information. And here's an example of what this, for example, does. Here on the left-hand side, you see a manifold embedding in 2 dimensions of subjects which have just been, similarities have just been learned based on imaging information alone. If you try to find a separation between the red points and the blue points, it's very hard to do. On the right-hand side is a result of what happens if you add more information from the genetics. You can clearly see that the blue points are now better separated from the red points, and it's easier to classify them correctly. Okay? So I'm going to skip a few slides because that's something I'll probably discuss with some of you in the reading group later on. But I just wanted to give you a few more references which are useful to look at. And I think I should also acknowledge quite a lot of the PhD students, postdocs, who did quite a lot of the work which you saw here in the second part of this talk. And also I should acknowledge the funding bodies who funded this research. And if you have any questions, I'm very happy to answer any questions.